In this session, we will continue the content in the previous sessions. We see the definition of e.g. Let me write this for you again. We call that EG equal to let rho from G to CLE, okay, GLE of E be a representation we define EG equal to the set of all vectors in E such that for any G in our group, rho G of V equal to V. Now, if EG be a finite rank subspace of E, for example, EG have V1, Vn as a basis, then Kn is isomorphic to EG. And we see that if we consider identity map from Kn to Kn, and also identity map from EG to EG, and this phi consider by these function rules. for any sigma alpha IEI in Kn. Also, the base of Kn be E1, E2 and En. Okay, so any element of Kn is a linear combination of the spaces. For any element of Kn, we define phi of this element equal to this linear combination of element in E or Eg. We know that this is an element of Eg, and Eg is a subset of or subspace of E. So E1 must map to V1 and En to Vn. Okay. If we consider trivial representation, rho from G to GLE be a trivial representation, rho of G equal to the identity map for any G in G. So we can write this rho of G, okay, and this rho of G equal to identity map. Then we see that phi of we can consider two representation, one from Kn, one from Eg. Rho 1 of G of any element in Kn, such as this, equal to C of this, because this is the identity map. And this is equal to phi of this equal to this summation and this is equal to rho 2 of G of this element. because row 2 is again. So this diagram is commutative, and we have these equalities, okay? Phi of row 1 of G of V equal to row 2 of G Phi of V. And also in this example, let's V belong to EG, okay? Then we have this sub-representation we have the following homomorphism from K to E, from K to E. Consider this function by these function rules. Phi of t equal to tv. T is an scalar number, so that the range of this linear function is a one-dimensional subspace of E, okay? Now we see that if we consider this diagram, we have for any t, for example, we have V of I of G of V, and for any G, okay, for any G in G and for any T in K, this is equal to this is, so that T in K, this is phi of T, and this is TV. What we can write this TV equal to T of rho of V rho of G of V, because we know that V is an element of EG, okay, so that for any G in G, rho of G of V equal to V, rho of G of V equal to V, and this is equal to rho of G of TV. And this is equal to rho of G of phi of T. So that we have this equality again. And so this is a homomorphism. This holds because V is an element of EG, and this holds because rho of T is a linear map. Okay. So we have this example in our book. For any element of EG, we have a homomorphism from K to E. In our book, K denoted by 1, okay? And also any homomorphism indicate an element of EG, because if Please note that if Phi, for example, belong to this homomorphism, then for any T in K, and for any G in G, we must have this equality. Phi of I of G of T equal to rho of G of Phi of T. Or equivalently, Phi of T, because this is identity map, equal to rho of G of Phi of T. This shows that this element, if we denoted this by V, for example, this V must be belong to E of G, or E to the power of G, so that if we consider 1, for example, this holds for all T. If we consider 1, Phi of 1 is an element of EG, so that this is a 1-to-1 and onto, or a bijective. It is a bijective identification. And also we have this lemma Before this, I recall that the definition of normal subgroup definition let H be a subgroup of G H is called normal if and only if for any G in G and for any H in H, G inverse H G belong to H. Or equivalently, H is normal if and only if for any G in G, GH equal to HG. Okay. It is very trivial. If we have this, G inverse HG must be equal to H and vice versa. Now we can see this lemma invariance under normal subgroups. Lemma let G be a group and H be a normal subgroup of G. Okay. Then for any representation rho, for example, from G to GL of E, the subspace EG equal to the set of all elements rho H of V equal to V for all H in H. So we write EH. Okay, EH for all H in H, rho H of V equal to V is a sub representation of E. And its proof is easy. Because this is an invariant subspace of E. Let V belong to EH and G belong to G. We want to check that rho G of V belong to EH again. Let we denote this rho G of V with W. Then for any then we know that rho H of V equal to V for all H in H. So for any H in H, if we consider H in H, we see that rho H of W, because we want to show that this element is belong to EH, so rho H of this element must be equal to V. Rho H of this W equal to rho H of, let me write this for you, rho H of W equal to rho H of this element, rho G of B, and this is equal to rho of HG, because rho is a homomorphism. And this is equal to rho of GG inverse HG, because this is identity element, okay, and this is equal to rho of G multiplied by rho of the inverse of GHG of V. But we know that this is an element of H, because H is a normal subgroup. And so rho of this element of V equal to V, so that this is equal to V, and this is rho G of V, and this is our W. Okay, so for any H in H, rho H of W equal to W, rho H of W equal to W, so that W must belong to E H. And we have this example, regular representation, that we omit this. Let me define quotient, kernel and image. Quotient, quotient explicit, I must write 1 O, okay, OU. Quotient. Let row from G to GLE be a representation. And if be an invariant subspace of E with respect to row, okay. Then we can define row tip, for example, from G to GL of EF, this quotient space as a representation. by this function role. For any G, in G we define and for any V in E we define row tilde G of VF equal to rho G of V. Please note that for any G in or group G row tilde of G must be a linear injective function from this quotient space to itself. Okay, so we must define rho tilde of G for any element of this quotient space, and we know that this quotient space equal to the set of all left cosets such as this, such that we belong to E. And this function, by this function rows, is a well-defined function. This is a well-defined function. Because if V1 F equal to V2F, we see that V1 minus V2 is an element of F. And this shows that for any G rho G of V1 minus V2 is an element of F. Because this is an invariant subspace. For any element of F, rho G of this element must be belong to F. And this shows that for any G in G, rho G of V1 minus in this definition we must define this rho tilde of G of Vf equal to rho of G of Vf. This we must consider this coset of F. This shows that rho G of V1 minus rho G of V2 of F equal to F. And we know that F is equal to the zero element of this quotient space. Okay, so if V1F equal to V2F, we prove that rho of for any G in G, rho of G of V1 minus rho of G of V2 of F equal to 0 of this quotient space, so that these two must be equal for any G in G. Rho G of V1 of F is equal to rho g of v2 of f, and this shows that for any g in G, rho tilde of G of Vf is equal to rho tilde of G of V2. Okay, so this is a well-defined function. So we need this property that F must be an invariant subspace of E. And also we know that if we consider the quotient map from E to this quotient space, that we denoted by phi. Okay, phi of V equal to Vf. Okay, for any V in E, and for any G in G, this is rho of G and this is rho tilde of G. Okay, then we see that for any G in G, and for any V in E, we have phi of rho G of V equal to phi of this equal to this left coset of F, so that this is rho of G V F. And by our definitions, this is equal to rho tilde of G of VF. This is our function. Please note that this is our definition. Rho G of V of F equal to rho tilde of G of VF. And this is equal to rho of G of phi of V. Sorry, this is rho theta. Okay, and this is equal to rho tilde of G of phi of V. And so we see that phi of rho G for any G in G and for any V in E, phi of rho G of V equal to rho tilde of G of phi of V. And we have this identity again. We have this identity again. This is rho in our example and this is rho tilde, okay? E1 is E and E2 is the quotient space E divided by F. Okay, dear students, كانت هذه الجلسة الأخيرة من دورة التحليل التوافقي. But the operator theory class will continue. Do you understand? This is very important. لكن درس نظرية المشغل سيستمر. Do you understand? Muhammad Hassan? Okay. And also let me recall that and I will send some offline sessions for you for harmonic analysis class, okay? Okay, thank you very much. The operator theory class after 50 minutes, okay? Okay? Okay, goodbye for now. Goodbye.